A system of equations is a set of two or more equations, and for our situation, we are going to look at equations with two variables, x and y. So each of these equations can be graphed, and when you graph lines, it's possible to have three different outcomes. The first situation is where the two lines intersect at one point. So we're going to look at this system. Y is equal to 3x and y is equal to negative x plus 4. If we graph these equations, the first line is in slope-intercept form. And we can see that this line has a slope of 3 and a y-intercept of 0. So because there is no y-intercept here, we can assume it to be 0. So we are going to anchor this line at the y-intercept of 0, and a slope of 3 means it goes 3 units up for every 1 unit over. And so we can graph these 2 points and draw the line. For our second equation, y is equal to negative x plus 4. We see that our slope is the coefficient of x, which is equal to a negative 1, and our y-intercept is 4. So we are going to anchor ourselves at the point 0, positive 4 at the y-intercept, and then draw a line with a slope of negative 1, which means that in the numerator, the negative 1 indicates that we are going to go down 1 and 1 to the right. So again, starting at that anchor point of 0, 4, we draw going down 1 and 1 to the right, continuing down 1 and 1 to the right, and so on until the line is drawn. We see here a single point of intersection, and if we were to assign coordinates to that point, those coordinates would be 1 unit in the x direction. So we'll make the ordered pair 1, and if we count up, it's 3 units in the y direction. And so we have the point 1, 3, which is our single solution. And so in this situation, we have one solution. And the system is what we call consistent, which means that there is a solution. The equations are called independent, which means that they don't mimic or follow each other. For our next system, we're looking at these two lines, y is equal to x minus 1 and y is equal to x plus 3. These lines both have a slope of positive 1 because the coefficient on x is 1. But for the first line, we have a y-intercept of negative 1, and with the slope of positive 1, we can draw the line. For our second line, we also have a slope of positive 1, but this time the y-intercept is at positive 3, so we're at 3 units on the y-axis, and we can also draw this line. And looking at these two lines, we can see that there is no point of intersection, and so there is actually no solution to this system. Because the system has no solution, we can see here that it's impossible to be on both lines at the same time, and so we say that the system is inconsistent. However, because the two lines do not follow each other, we say that these two equations are independent. In the third situation, we have two equations, y is equal to x, and 3x minus 3y is equal to 0. Graphing the first line, it has a slope of 1, the coefficient of x is 1, and it also has a 0 y-intercept. So we will graph this line, again realizing that it's got a slope of positive 1. For the second line, we could also isolate the y and get it in slope-intercept form, but we could graph this line by plotting points. And so I think that's what I'd like to do here. We have 3x minus 3y is equal to 0. Next, what I'd like to do is to plot some points by making a table of values. So for example, if I chose x is equal to 0, we can calculate the y value. So 3 times 0 minus 3y is equal to 0, and this term drops out. So we get negative 3y is equal to 0, or that y is equal to 0. If we choose another point, for example, x is equal to 1, then we get 3 times a positive 1 minus 3y is equal to 0. And when we set 3 times 1 is 3, and add on the 3y to the other side, we end up with positive 3y. And so in this case, y is also equal to 1. So now we can graph these points, 0, 0, and also 1, 1. And when we draw the line, we can see that this line is the same line as the other. And therefore, there are many, many points that lie on both lines at the same time. And as a result, there are infinitely many solutions. And because there are many solutions, and there is at least one solution, we say that the system is consistent. However, because the two lines are identical to each other, whenever we encounter a system of two equations and two unknowns, we're usually looking for a single solution, as in the first case, where we had a single point with the coordinates 1, 3. However, sometimes the way that the equations work out is that when you try to solve the system, you will end up with an inconsistent system that gives you no solution, or potentially a set of dependent equations where the lines lie on top of each other and you end up with infinitely many solutions. So you do need to be on alert for the special but unusual cases.